Okay, so we are going to look at Chapter 3, problem number 32. So this problem reads, Jim's dog Sparky runs 40 meters northeast to a tree, then 70 meters west to a second tree, and finally 20 meters south to a third tree. Draw a picture and establish a coordinate system. Calculate Sparky's net displacement in component form. And then calculate Sparky's net displacement as a magnitude at an angle. So we're going to have to make a couple assumptions about this problem, and that has to do with what northeast is. Since it doesn't give us an angle north of east or east of north, then we can make the assumption that that angle is at 45 degrees. So it's just purely northeast, right along that midline between north and east. So let's first draw a coordinate system and then draw our vectors on there to visualize what this motion of Sparky looks like. So that's part A. So we will use our normal coordinate system. I kind of like this coordinate system. It's the one we're all most familiar with. So here is our XY coordinate system with the positive x-axis to the right. It tells us that Sparky runs, and we're going to have him start here at the origin. He runs 50 meters northeast to a tree. So again, along that line that divides north and east directly. So 50 meters northeast to a tree. And then 70 meters west to a second tree. So the length of that arrow is going to be longer by 20 meters, and it's going to be straight west. So this has a total of 70 meters, and it's purely horizontal, or at least it's supposed to be. And then he runs, I have to find the problem again, 20 meters south to a third tree. So this is a smaller vector, not as big as this one, certainly not as big as that one. So here is our 20 meters south. So that's sort of his pattern of his vectors. Now, of his displacement. Now we're going to call this vector A. I'm going to call this one vector B. And we will call our green one vector C. That sort of gives you that coordinate system and the vectors along that coordinate system that we could draw that picture for. That's part A. Part B says, what are the vectors in component form, or the resultant vector? So we have to look at, to get the resultant vector in component form, or just in its x and y coordinates, as we've been doing, then we have to add all the x coordinates, components, and all the y components of the three vectors. So let's look at vector A first. Vector A has magnitude of 50 meters, and it has an angle of A of 45 degrees, right between north and east, so that northeast value. So the x component is our hypotenuse, our magnitude, times the cosine of the angle. So we have 50 times the cosine of 45, and that gives us 35.4 meters. Our y component is A times our magnitude times the sine of the angle. So we have 50 times the sine of 45, and as you all know about 45-degree angles, their components are the same. So there is our x and y components for vector A. So let's look at vector B. Vector B has a magnitude of 70 meters, and angle of B is, right, well, we can take that vector and we can put it right on that x-axis to know that it's angle, and it's purely to the left. So an angle to the left is 180 degrees. Now we can also do a little bit of intuition on this one. It's just pointing to the left. There's no up or down. So we know that it's all x and doesn't have any y. But our angles in our calculation should also tell us that. So our x component should be the magnitude of the angle times, the magnitude of the vector times the cosine of the angle. So 70 magnitude times the cosine of 180, and that gives us minus 70 meters. So pointing to the left, and in fact it's going west, or we'll call left-west. And our y component, we should know, if it's just purely horizontal, there's no y component, but it should also work out for us. So the sine of angle B, so 70 times the sine of 180, we know to be 0. So the sine of 180 is 0, so there is no y component. And our last vector is vector C. It has a magnitude of 20 meters, and angle C is, well, it says it's straight south. Straight south can be thought of as either as negative 90 degrees or 270 degrees, and I sort of like doing things relative to the x-axis, so it makes my trigonometry nice and slick. So that's 270 degrees. So our component, our x component is C times the cosine of angle C. So that is 20 times the cosine of 270. And that is 0. We know that if it points straight down, it does not have a x component. Our vertical component is C times the sine of the angle. So we have 20 times the sine of 270, and that gives us negative 20. It should be pointing down, and so it's going to be negative because it's south. So now if I want to find the x component of the resultant and the y component of the resultant, I add up all the x components and add up all the y components. So we'll call our resultant vector D. So dx is going to be a sub x plus b component in the x direction plus vector c in the x direction. A is 35.4, b is negative 70, and c is 0. So my x component for vector D is 34.6 in the negative direction. So negative 34.6 or 34.6 to the west. My y component is going to be the component of y for vector A, the y component for vector B, and the y component for vector C. So vector A is 35.4 plus vector B, which is 0, plus vector C, which is minus 20. My y component is 15.4 meters, or north 15.4 meters. So those are the x and y components of the resultant vector. The final question is is the magnitude and the angle. So I use my Pythagorean theorem for that. So the magnitude of D is going to be the square root of d sub x squared plus d sub y squared. So that equals d sub x squared is negative 34.6 squared plus d sub y is 15.4 squared. And I get a magnitude of 37.9 meters. The vector is not just a magnitude, but also an angle. So my angle, will you remember, is the inverse tangent of d sub y over d sub x. My inverse tangent of d sub y is 15.4. D sub x is negative 34.6. And I get an angle of, let's check that one. I'm not sure that, I don't know why it's not here, but I don't have it. So the inverse tangent of 15.4 divided by negative 34.6. That on our calculator gives us an angle of negative 24 degrees. Now, this is where we have to always be careful. Is it really negative 24 degrees? That means it is in quadrant number 4, negative 24 degrees. So we want to make sure we look at our x and y components. Our x component is negative. Our y component is positive. This tells us that it should be, with a negative x and a positive y, it should be in quadrant 2. But negative 24 isn't in quadrant 2. Negative 24 is represented right here. That's negative 24. That's the same. We'll get the same tangent value for the vector in that direction, which it looks a lot more like it should be for our resultant vector. So how do I get the actual angle? Well, this would be 180 degrees. That would be a full 180. And I'm 24 degrees less than 180. So I subtract 24 from 180, and I get 156. So we want to be very careful how we determine the angle of our resultants. We always have to make sure that it is consistent with the positive and negative for our components. Just taking the inverse tangent will only give you the angle in quadrants 1 and 4. We need to make sure our resultant vector makes sense in quadrants 1 and 4, and if it doesn't, we need to adjust that angle by 180 degrees. In this case, we subtract that angle from 180. All right, good job.